Hello everyone, today we'll talk about the medicinal chemistry of the gastric acid secretion inhibitors. As you go through the notes, again I want to remind you any comments I add is just for your own um, learning, for your own reference, and you'll only be obligated with the notes written in this manuscript or this pre-class notes. Let me start by the objectives. I want you to be able to differentiate between the different mechanisms used for each class of the gastric acid secretions. We actually have two classes, and then the H2 receptor antagonists and the proton pump inhibitors, and they added a small note about the antacids and the chelation that occurs with the antacid, which is here in objective number 2. So hopefully you'll be able to explain the the interaction of the antacids with the antibiotics tetracycline and fluoroquinolone, and how the complex, or what's known as chelation, occurs. How the chelation occurs. And then understand the rationale of design of H2 receptor antagonist. There's a nice story for someone who won the Nobel Prize on his discovery for the H2 receptor antagonist in the notes, and then recognize the structural features. There's one structural feature in the cimetidine that's responsible for its horrible, well, not that horrible, but there is an adverse effect that could be avoided, and drug interactions that could be avoided because of one structural feature that once replaced, all these effects and interactions will be removed, and the H2 receptor antagonists become a really nice and selective um, um, class of medications to help um, inhibit the secretion of the acid. And then be able to compare between the H1 receptor antagonist and H2 antagonist structurally and pharmacologically, how the difference in structure affects their activity and their side effects. And then explain the mechanism of activation for the proton pump inhibitor. I do not expect you to memorize or write structures or the mechanism of activation reactions, but just to get a general idea, or to get an idea about the general concept. And then discuss the reasons for the high selectivity of the proton pump inhibitors, and then relate the metabolism of the proton pump inhibitors to their drug-drug interactions, explain the reasons behind chiral switching in general and the chiral switching in the proton pump inhibitors, and finally explain why proton pump inhibitors must be formulated in the delayed release form, basically using an enteric coated form if they are to be given orally. Okay, so there are many ways by which the gastric acid secretion can be inhibited. By looking at this picture here, this shows a section of the stomach, and this shows the different ways of stimulating the secretion of the gastric acid. As you can see, histamine is one of these routes, acetylcholine, and the gastrin. Acetylcholine binds to the muscarinic receptors, so this might not be a good idea to inhibit this receptor because it's widely spread in the body and can have a lot of side effects. Gastrin, there has been a lot of research trying to use gastrin and inhibit this receptor such that it can lead to the prevention of the synthesis of the production of the gastric acid. But most important of all of these are the histamine and the final stage here, which is the proton pump here, that pumps the acid into the what's called canaliculi of the stomach. So today we'll talk about the antihistamine, basically the histamine receptor type 2, and we'll talk about the proton pump inhibitors. And in fact, these are the two most commonly used medications for inhibiting the gastric acid. Before we talk about these kinds of inhibitors for the gastric acid secretion, I just want to add a comment to the use of antacids with antibiotics. As you have seen in the notes posted by Dr. Yu and Dr. Dunn, the antacids, basically like the calcium hydroxide bicarbonate, all these antacids that uses the metals such as calcium, magnesium, aluminum, all these can lead to inhibition of the absorption of some medications, in particular the antibiotics. There are two types of antibiotics that can be inhibited by such antacids. The first one is the tetracycline here. This shows how the metal here is chelated, is forming this complex, or also called chelation, and this complex prevents the antibiotic from being absorbed, the tetracycline. The same applies here to the fluoroquinolones. The metal here is forming a chelation, a complex with the fluoroquinolones such as ciprofloxacin, for example, and this will prevent the absorption of these antibiotics and thus will lead to loss of antimicrobial activity. The metals that are responsible for this kind of chelations are examples of these metals are calcium, magnesium, aluminum, and there are also other metals such as the zinc and the iron, which are available in the multivitamins. So anytime a patient takes an antacid or a multivitamins, we should be cautioned if they are taking any of these antibiotics. The solution is to avoid taking these antibiotics with the antacid, or actually avoid the antacid during these antibiotics, or at least have 2 hours separation between the time you take an antacid or a multivitamin with any of these antibiotics. I should note also that these kind of metals that cause this complexation or chelation are the divalent or the trivalent metals. In other words, these are the metals that have +2 or +3 charges. The monovalent, such as sodium, for example, they do not cause such kind of chelation. Finally, all the acid reducers medications, whether they are antacids or whether they are H2 histamine antagonists or the proton pump inhibitors, all these antacids will reduce the acidity of the stomach, obviously, and for some drugs this might affect their absorption, because for some drugs their absorption might require that the stomach be acidic. Such drugs are the azole antifungals, the atazanavir, and some of the controlled release formulations. So this fact applies to all the gastric acid inhibitors.
Okay, so there are two classes that are commonly used as gastric acid secretion inhibitors. The first one is called the H2 receptor antagonists, or for short H2RA. These are histamine receptor antagonists. So let's first start by a brief introduction about the histamine and the type of receptors that the histamine can bind to. Okay, so histamine is formed by the decarboxylation of an amino acid called histidine. This is the amino acid here. It's histidine, and it's converted into the histamine by the removal of this carboxylic acid, and that's why the enzyme that does this conversion is called histidine decarboxylase. So this is the histidine amino acid, and then by removing the carboxylate group, it's converted into histamine, and the enzyme again is called histidine decarboxylase. And as soon as this histamine is formed, it has to be stored rapidly, otherwise it will be inactivated or metabolized. So the histamine is actually stored into vessels or granules such that they are protected from being metabolized.
So the histamine is stored into vessels or granules, and these granules can be found into 4 types of cells. The first two are called the mast cells and the basophils, which are types of white blood cells, and they are responsible for the allergy reactions that occur basically by the activation of the antibodies on the surface of these cells by an antigen that leads to the release of the histamine. These antibodies that are at the surface of the mast and basophils cells are called IgE. The other two types of the cells where the vessels that contain the histamine are found in are the CNS in the brain, and in this case the histamine acts as a neurotransmitter. And then the fourth type are the enterochromaffin-like cells, which are available in gastric glands next to the parietal cells in the stomach, and upon the release of the histamine, the gastric acid is released. All the information I provided so far is just to give you a brief introduction about the histamine, their synthesis, and their release. So based on what I said so far, you can imagine the ways where we could prevent the histamine action. One way would be preventing the synthesis of the histamine by inhibiting this enzyme. There are a couple of drugs available, but they are not commonly used. And another way is by stabilizing the mast cell, which are used to store the vessels containing this histamine, and these are called mast cell stabilizers. Examples of them are the cromolyn and the nidochromelin, and we are gonna talk about them when we reach to the allergies and the drugs used for allergies of the eyes. And the third type, which is our topic today, is by designing drugs that inhibit the histamine receptors. So let's talk about histamine receptors. There are four types of histamine receptors: H1, H2, H3, and H4 histamine receptors, and they are distributed in different parts of the body. The H1 histamine receptors can be found in the smooth muscles, endothelial cells, and in the brain, in the CNS. The ones in the smooth muscles are available in the bronchi, GI tract, and the uterus. And in the case of the bronchi, the release of the histamine causes a contraction of the bronchi, leading to bronchoconstriction, which is one of the signs for having the allergy. And the release of the histamine at the endothelial cells leads to the contraction of these cells and increasing the permeability of capillary walls, and increasing the blood flow to the extracellular spaces, and this process leads to the edema. In fact, it is because of the action of the histamine at the H1 receptor in these two sites that we end up having the allergic and hypersensitivity reactions that can also lead to what's known as anaphylactic shock. The third part where histamine can be found is at the CNS, in the brain, and in this case the release of the histamine from the vessels in the brain makes the histamine act as a neurotransmitter, and they can play a role into the neuroendocrine control, the cardiovascular regulation, and thermal body weight regulation, as well as the sleep cycle, and affecting things like the nausea and motion sickness. The second type of the histamine receptors are H2 receptors. They are found into the parietal cells of the gastric mucosa, and they regulate the release of the gastric acid. In fact, as we will see, in order to treat gastric acid reflux, we will be using products like H2 histamine receptors inhibitors or antagonists. The third type of the histamine receptors are available in the CNS, like the H1 receptors, and they actually regulate the release of histamine as well as other neurotransmitters. They act as an autoreceptors as well as heteroreceptors, which means they are located at the presynaptic cleft, and they are responsible for the negative feedback inhibition of the histamine synthesis and release, as well as other neurotransmitters such as dopamine, GABA, acetylcholine, noradrenaline, and serotonin. Finally, a fourth type of histamine receptors recently discovered play a role into the immune responses. Before we move into the next slide, I just want to say that the fact that we have more than one receptor available in different parts of the body is actually very advantageous in designing drugs to treat conditions like the allergies and the hypersensitivity reactions. Like in this case, we could design inhibitors for the H1 receptors that will take care of these symptoms of the bronchoconstrictions and edema resulting from the allergic reactions. We can also design drugs specifically for the H1 receptors to help with the sleeping aid and even to help with the nausea and motion sickness. And we can design certain drugs to target the H2 histamine receptors to treat the diseases resulting from the increased acid secretion. So I just want to say that this is a very unique case where you have different receptors distributed into different parts of the body, and then you can take advantage of that and design a selective toxicity, selective drugs. Reminds us of the concept of the selective toxicity and the magic bullet or the silver bullet that we spoke about in session 1. So this is an application that we see here. Before we move into the next slide, let's see how we could actually explain how one histamine, in the next slide we'll explain how one histamine molecule is able to bind to these 4 different types. Okay, so how can one molecule bind into these 4 types of receptors? I hope you still remember the case of the acetylcholine and how it could bind into 2 different types of the cholinergic receptors. One was a nicotinic and another was a muscarinic. And we explained in an exercise number 8, we created a video to explain how that same molecule can bind into 2 different receptors by changing its conformation through rotation into a single bond. This is an example. This is another example of this concept where this same molecule, the histamine, binds into H1 and H2 receptors through its trans conformation. So this is the molecule, this is the Newman projection, and you will see that the trans projection, the trans conformation is preferred for H1 and H2, while the gauche conformation is preferred for H3. So what about H1 and H2 receptors? How can one molecule bind to them? Apparently studies shows that for the H1 receptor, it requires only 2 of these nitrogens to be present. This here forms an ionic interaction. This one here forms a hydrogen bond. While for H2 receptor, there is another spot here in the H2 receptor that requires the presence of this nitrogen. So this same molecule binds to 2 different receptors by forming different types of interactions. And I just want to say there's not much known about how the histamine binds to the newly discovered H4 receptor.
Before we move further into the discovery of the H2 receptor antagonists, I need to switch gears and talk about something that will help for the rest of the lecture, which is just a brief introduction about the metabolism and the metabolic enzymes and the factors that affect the metabolic enzymes. So drugs or foreign chemicals in general are metabolized, basically modified through um, reactions that are catalyzed by some enzymes. So reactions that are facilitated by some enzymes would modify these drugs or foreign chemicals mainly in the liver, but they can also be metabolized or modified in the blood, the gut wall, or the lung, or some other organs like the skin, for example. And the purpose of this metabolism or modification is to remove the toxic effect of these chemicals. And then the resulting products of this metabolism are called metabolites. And they are usually less active or inactive, except um, for the case of prodrugs, as we have seen with the enalaprilat. Actually, the enalapril was metabolized by the esterase enzymes and was converted to active, but this is an exception. Most of the cases, drugs, when they are metabolized, they are converted into the inactive form. And so the um, the goal of the metabolism would be, number one, detoxification, number two, converting the drug into less active or inactive, and then number three is to increase the aqueous solubility of the drug by making it more polar, and this way it could be easily excreted, which is number four. It would be easily excreted through the urine. So the urine is actually um, um, has the nature similar of water, and so by increasing the water solubility, making the metabolites more polar, the um, these metabolites will be easily excreted through the urine. They dissolve better in the urine, and then they can be easily excreted. So this is generally the goal of the metabolism. Now, metabolism, like we said, is a reaction. It's catalyzed by some enzymes. Among these enzymes that are responsible for catalyzing, or in other words, facilitating these reactions, is what's known as cytochrome P450, or we refer to this enzyme by the term CYP. Okay, so the CYP is responsible for catalyzing the oxidative reactions. So the majority of the reactions that occur for the drugs are actually oxidative reactions. So CYP is responsible for the oxidation, and it is actually the major enzyme that's involved in drug metabolism, responsible for about 75% of the total metabolism. Okay, so if we compare this enzyme to other enzymes like esterases, amidases, and other kinds of enzymes, then this one um, is responsible for about 75% of the metabolic reactions. Okay, it's available in various forms or various isoforms, which we refer to them as isozymes. Okay, so enzymes, cytochrome P450 is an enzyme, but it actually is available in different forms. We call them isozymes, and these isozymes have different substrate selectivity. These isozymes have different substrate selectivity, and the term substrate means anything that binds an enzyme usually is called a substrate. Okay, so these isozymes would have different selectivity to different substrates. So maybe one of the isozymes could prefer to oxidize, for example, an ethyl group, while another enzyme might prefer to oxidize maybe an amide group, something like that. So the CYP is available in many forms that are called isozymes. There are about 50 of them, but the most common ones are the CYP3A4 and CYP2C9 and CYP2C15. So why is this important? Why are we bringing this topic here in the middle? Because I want to give you an idea about the CYP enzymes. Any time we refer to CYP3A4 or CYP2CA or any of these, then you would recall that it's a metabolic enzyme responsible for oxidation. And also, we will talk about we will need to know the interaction of these enzymes with drugs and food, um, as we'll see later. So some drugs or certain foods might be able to increase or decrease, basically either enhance or decrease the activity of these isozymes. Okay, and since these isozymes are responsible for metabolism, so as you can imagine, if we increase the activity of these enzymes, then more amount of the drug will be metabolized. Okay, so then the effect of that drug that is metabolized will be reduced. So if we have a substance or drug X that increases the activity of certain isozyme, then all the drugs that are metabolized by this enzyme will be actually affected, and their metabolism will be reduced, and their metabolism will be increased, and then you will have less amount of the drug available, you will have less pharmacological effect. These types of chemicals or drugs that increase the activity of the CYP isozymes, we call them enzyme inducers. Okay, the process is called enzyme induction, and these chemicals are called enzyme inducers. The other kind of substances or drugs or foods that inhibit the activity of the CYP enzyme are called enzymes inhibitors, and so the process is called enzyme inhibition. And then, so in the case of the inhibition, of course, would be the opposite would happen. If you inhibit the cytochrome P450, if you inhibit the CYP enzymes, then they are not going to be able to metabolize the drugs. Then more drugs are going to be available in the plasma, and the drug concentration in the plasma will be higher, and you will have more toxic effects, side effects from these drugs. Okay, so these changes are the major source of drug-drug interactions. We will visit this again later, but for now, just briefly, wanted to give you an idea about the CYP, the drugs that can increase or decrease the activity of these enzymes, and these are the major source for drug interactions. So how do we manage such drug interactions? Again, this is brief answer or brief description of how you manage the drug interactions, but we'll talk about this more in details. But just briefly, if there's a drug interaction, then you basically can adjust the dose. So for example, if drug X would cause an increase in the inhibition of drug Y, then increase of the metabolism of drug Y, then you want to administer more of drug Y. And the opposite is true. If drug X reduces the metabolism of drug Y, then you're going to have more of drug Y in your system, so you want to adjust the dose and give less of the amount. So one way is adjusting the dose. Another way is simply just choose a different drug. Okay, so if you have a list of drugs, one of them interacts with the drugs that the patient is currently taking, then you just want to choose a different drug. These drug interactions are very important in cases where we have patient taking drugs that are important for their health. Let's say that somebody is taking a blood pressure medication forever, and so then if you want to administer another drug, then you want to pay attention to selecting one that does not interact with this blood pressure medication. Drug interactions are also important in cases where some side effects could be serious, like for example, warfarin is very sensitive drug. If you increase it or decrease it, it might affect, might produce side effects, or might produce less effect. This is also important for cases of the narrotherapeutic index drug. If you don't know what the narrotherapeutic index drug, it's okay. You will learn about it in the pharmacokinetics. Finally, I just want to say that the CYP enzymes can actually vary from individual to another. They can actually vary from one race to another. So this variability also affects the drug metabolism and the drug interactions. This is something that Dr. Jones will um, discuss more under the topic called pharmacogenomics. Okay. So now we could go back and talk about the H2 receptor antagonists, and we'll start by the discovery of the H2 receptor antagonists.
Let me start by the discovery of the H2 receptor and their antagonists. In around the 60s, they realized that the histamine induces the gastric acid secretion and the allergies reaction. But antihistamines, although they inhibit the histamine from binding to its receptor, they inhibit the allergic reactions, but they were not able to inhibit the gastric acid secretion. Back then, they did not know if they have more than one receptor or just one. So they hypothesized that there must be another receptor that's responsible for the secretion of the gastric acid. This receptor, indeed, the H2 receptor, as we will find out, is different from the H1, and the H1 antagonists inhibit only the H1 receptor. They do not inhibit the H2. That's why they couldn't stop the gastric acid secretion. So to find out how a new molecule can be designed, they tested hundreds of molecules on the receptor that was known back then as only the histamine receptor. The theory was not being proved yet. Among the molecules that were tested was these two molecules. First, they started with the imidazole, and as you can imagine, there are plenty of options that they tried, but one of the two trials have led to the discovery of the antagonist. So this is the imidazole here, the original endogenous molecule that binds to the histamine, and it binds to the agonist site. And then there is an antagonist binding site for the H2 receptor that has been hypothesized. And then when they tested the first molecule by extending this chain to 3 atoms, they found that this molecule has a partial agonist, which means that it binds as an antagonist and as an agonist, and overall result of binding of this molecule was a partial agonist. So they extended the chain further and made it 4 atoms for the length of this chain, and they noticed that this molecule is no longer working as an agonist because it cannot bind to the agonist binding site, but it can work to the antagonist. And further modifications of the drug has led to this molecule, which was derived from these experiments. So they have the imidazole, they maintain the imidazole ring, they added a methyl group here to increase the selectivity for the H2 receptor. They extended the chain, they kept the sulfur here because it's actually able to increase the potency as an electron donor group. That's actually as an electron withdrawal group. It increases the potency for the binding to the H2 receptor, and they added this group here that led to the elimination of the quaternary ion here. So apparently they found that the ion is not the preferred one. Actually, a polar group forming dipole-dipole interactions and hydrogen bond was more important and valuable. And the first compound discovered was called the samidadine, also sold under the name Tagamet. The 200 milligram is actually the OTC, available OTC, but the 400, 600, 800 are available through prescription. The discovery of this H2 antagonist led to Sir James Black to get the Nobel Prize in Medicine in 1988. In fact, he got this prize for his work on the
discovery of the cimetidine as well as the propranolol, which is a beta blocker that we'll discuss later with, in cardiology. The discovery of the cimetidine was a breakthrough at that time, and this drug was being used to treat cases like peptic ulcer and gastric ulcer, GERD, for a long time, from the 60s until the 80s. But then a new agents were discovered. The reason for the discovery of new agents was because of the many side effects that cimetidine has, plus the drug-drug interactions. Cimetidine has anti-androgenic activity, leading to increased effect of the estrogen. So in women, they will have galactorrhea and amenorrhea, while in men, they will have the gynecomastia and impotence. It also can cause somnolence and confusion in some elderly patients with decreased renal function and in people with decreased renal function. It also inhibits some of the cytochrome P450 isozymes and thus increase the concentration of agents that are metabolized by this enzyme, in particular the neurotherapeutic index ones such as phenytoin, thiophalin, some of the benzodiazepines like diazepam, warfarin, and quinidine. And it inhibits the renal tubular secretion of some drugs such as procainamide, and this of course will lead to the increase of the concentration of procainamide in the plasma. And finally, it has a short duration of action from 4 to 8 hours, which therefore requires more frequent administration of the drug. Apparently, many of these problems, side effects, and drug interactions were because of the imidazole ring in the cimetidine. Here is the cimetidine here, and this is the imidazole ring. So therefore, by replacing this ring by another ring such as the furan ring or the thiazole ring, and the addition of some groups such as the diamine aminomethyl, and the guanidine, which actually would cause the ring to become more basic. So the addition of these rings, by replacing the imidazole, we were able to solve all these side effects. So we got rid of the adverse effects, the first two, as well as we were able to avoid the inhibition of this enzyme, cytochrome P450. So these agents, these three, the ranitidine, nizatidine, and the famotidine, they did not cause any of these side effects, and they did not cause any of these interactions. Plus, they also have a longer duration of action. We should notice here that besides the fact that we got rid of all these side effects, the affinity or the potency of these molecules have increased. With the cimetidine, we had to administer 200 or 400 or 600 or up to 800 milligrams of the drug daily, while with the other drugs we have, in the case of the ranitidine and the nizatidine, we have we can achieve the same goal by administering lower dosage, such as 75 or 150 milligrams, and these drugs were 10 times more potent. And with the recent drug, the famotidine was the best. It was the most potent. The potency was 30 times more than the cimetidine. So the drug was administered in dosage such as 10, 20, and 40 milligrams. This drug also has a longer duration of action. I just want to add that the acid actually has been discontinued. So this one here is no longer available in the US, and the most commonly used are ranitidine and famotidine, and Obviously, the samidine has too many side effects, so it's not commonly used, although it is still in the market.
Next, let's talk about the structure-activity relationships for the H2 receptor antagonists. This shows the general structure or the general pharmacophore for the H2 receptor antagonists. So, first of all, we should have a spacer of about 4 atoms between the nitrogen here and a ring, a heteroatomic ring. And the X here could be a sulfur or could be a CH2. On the left side here of the spacer, we should have a heteroatomic ring, such as the thiazole, the furan, okay, and like we mentioned, the imidazole would cause a lot of side effects, but that's still a valid ring. And then the ring should be attached to a group such as A, which is optional because A could be hydrogen, or it could be CH2, nitrogen, and 2 alkyl groups. And then the Y here could be a sulfur, nitrogen with a cyanide, or a CHNO2. Okay, and the Z, which is here part of the heteroatomic ring, could be a carbon, nitrogen, oxygen, or sulfur. So if you actually think about all these examples, they all match this structure activity relationship for the H2 receptor antagonists.
The second type of the gastric acid secretion inhibitors are the proton pump inhibitors. If this is the lining of the stomach, and this one here is the parietal cell, as you can see, there are 3 receptors up there that we spoke about earlier. You have the histamine, which we discussed as one of the classes, the commonly used ways of preventing the gastric acid secretion, and we said that these 2 are not preferred. The other class of the commonly used gastric acid inhibitors are the proton pump inhibitor. So this is the pump here, and this is the parietal cell. So right after the proton or the H plus is synthesized through an enzyme called carbonic anhydrase, the proton should leave the cell immediately, and for 2 reasons. First, if it stays in the cell, it can damage the cell, it can increase the acidity of the cell, and the second reason is the reaction that is responsible for the creation of this proton is reversible. So if the proton stays inside the cell, it can inverse the reaction. You might actually think about the enzyme that catalyzes the reaction of the synthesis of the proton, which is the carbonic anhydrase, and then think of it as a way to prevent the synthesis of this proton. But this is going to be not a preferred way because it's not as selective. Anyway, this is all just some additional information. What we really care about the most is first, the inhibitors of the H2 receptor, which we have discussed already, and then second, the proton pump inhibitor here. So as soon as the H plus is synthesized, it's immediately excreted from the parietal cell, and there is a space, it looks like a gulf inside this cell called the canaliculus. So the proton is excreted immediately inside this space, the canaliculus, and with the increasing amount of the H plus, the pH here is very low. It's less than 2 pH for sure, but it's less than 1 as well. So the pH here would be less than 1, and then the acid is accumulated and then is excreted from this canaliculus out into the lumen of the stomach. Okay.
The pump that is responsible of excreting the proton or the H plus is actually an enzyme, and the name of this enzyme is called the H plus K plus ATPase. The reason it's called H plus K plus because anytime it excretes an H plus, it actually takes inside a K plus. So there's always a balance between these two. And in fact, the K plus, after it goes inside, it goes here into a circle and is excreted again along with the chloride. So just something to consider or think about. But what we need to worry about is the enzyme that actually is responsible for excreting the H plus and taking the K plus, so that's the name, H plus K plus. ATPase because it actually breaks the ATP to ADP. So adenosine triphosphate is broken into adenosine diphosphate. Basically a bond is broken. This way this enzyme is taking its energy, the energy required to push the H plus and outside the cell. As you can imagine, with having too many H pluses here, it requires an energy to push the H plus against its gradient, concentration. So this is where the energy comes from. So that's the name of the enzyme. It's called adenosine triphosphate enzyme, the H plus K plus ATPase, which is also the proton pump. Now, the inhibitors bind to this enzyme covalently, which means that they bind irreversibly to this enzyme. When they bind to this enzyme, they inhibit this enzyme or this pump from working, and that's how they prevent the excretion of the H plus. What's unique about the fact that it binds covalently and irreversibly is that now these drugs will have a longer duration of action. If you remember, duration of action is typically affected by some factors such as the elimination T half-life and the minimum concentration and the absorption. In this case here, the fact that the proton pump inhibitors bind to this enzyme irreversibly or covalently means that it's gonna stay with this enzyme forever. It's not gonna leave it until this enzyme is actually recycled, damaged, and then a new one is made. So the time it takes for this enzyme to be replaced with a new one would extend the duration of action such that it's longer than its elimination T half-life. It's by far longer than the elimination T half-life. I'm not sure if you remember when we spoke about the MO inhibitors, and we said that it takes about 14 days for the enzymes to be replaced. Just to give you an idea, this is similar, except I'm not sure how long it takes for the enzyme to be replaced. I think it's few days, but I'm not confident about that. I'm only 50% confident that it takes only a few days for the enzyme to be replaced. It's definitely less than 14 days. Anyway, so this is an advantage where which makes the drug to be administered only once daily, which makes it very convenient. If you remember, in the case of the H2 inhibitor, we had to administer drug more often. But here the drug is only administered once a day because of the fact that it's irreversible and it's covalently bound to this pump. Okay, so there's a note here: synthesis of new pumps is required as the enzymes are naturally destroyed. Yes, of course, the enzymes are actually continuously destroyed and then are replaced with the newer ones, and then the continual administration of this drug will again binds to the receptor to inhibit them. What's unique about this method is that it's at the terminal stage of the production of the acid. What does that mean? It means that if we only inhibit the H2, then there is other ways to activate this the synthesis and the production of the H plus, the acid. But what's unique about the proton pump inhibitors is they actually block this final stage. So even if you have stimulants from this receptor or from that or this, the fact that we block the final stage here guarantees that there are no any other ways this acid is going to be synthesized. So that's what it means, what makes this drug unique. And as a result of that, in fact, this method of inhibiting the secretion of the gastric acid is much more significant, more effective than the H2 antagonist. It's able to reduce the gastric acid secretion by up to 99%. Okay. Let's talk about the pharmacophore and the structure-activity relationship for the proton pump inhibitors. This shows the skeleton for the proton pump inhibitors. We have 4 products here, and there is actually only 2 of them are over the counter. The Prevacid, actually 3, Prevacid, omeprazole, and the esomeprazole, the Nexium, Prilosec, and Prevacid are over the counter, and the rest are prescription ones, as far as I know, unless something else has changed and became an OTC. But since we are talking about this class of medication, I'm going to cover all these drugs as well. So the pharmacophore for all these agents, if you look at all of them, they all share the same skeleton, where they have the pyridine ring, and then they have the benzimidazole. This is the benz, and then the imidazole ring, and they have a linker which is a methyl sulfonyl. So all of them are going to have the same structure. And there is also an alkoxy group. I'm sorry, I just realized that this one here is not in the same place with the others, but I'm sure you can figure this out by yourself. So this should be like flipped on this side. Anyway, so but it's the same structure. This is the skeleton for the proton pump inhibitors, and you'll notice that in all of them you will have an alkoxy group. Alkoxy means, either an alkyl with an oxygen. This alkyl could be methyl, or in this case trifluoroethyl, or whatever this group is. It should have an oxygen and then attached to some alkyl group, and this was found, the alkoxy was found important to stabilize this molecule. So they all share the same skeleton, and the other substituents here are important. They are found important to avoid a side effect that this drug has initially, which was inhibiting the iodine uptake. But just you could ignore this information if you don't want to. So we'll focus on the skeleton, and which is actually common among all these structures. There's one thing I want to point out here, which is this sulfur here is actually chiral. Now, for you, or I mean, like if you remember, a chiral atom should have like four different substituents attached to it, and then like in the case of a carbon, and then you'd consider this a chiral. Here you have 3, so apparently the 4th one is actually this lone pair of electrons. So now with this lone pair of electrons, you have these 4 attachments to the S, to the sulfonyl, which makes it a chiral. In other words, you could arrange these in a different way and have a different isomer. So that's why with all these products, you will see that there is an enantiomer for them. That's why, for example, the omeprazole, you have the racemic mixture, which contains both enantiomers, the R and S, or both isomers, R and S, while the esomeprazole, the Nexium, has only the S enantiomer. And then the same is true for the lansoprazole. You have 2 products for this molecule, one with the racemic mixtures of both the R and S, called the lansoprazole, and then if we select only the R enantiomer, we could use this product, Dexlant. And we're going to discuss soon why do we select one enantiomer versus the other. Okay, these 2 are also available as enantiomers, but not in the States. You can find them outside the States, the United States, but we don't have to worry about that. Okay, and let's see. Okay, let's now talk about the mechanism of activation for the proton pump inhibitors. Apparently, these molecules are actually prodrugs, which means they are inactive, and they need special environment to become active. The environment for which these molecules are activated in should be acidic. Anytime the pH is less than 4, these molecules are activated and become active, and they are activated through this mechanism. I do not expect you to memorize any of these structures or reactions. The only thing I want you to pay attention to is that in the presence of a high acidic environment, pH below 4, and the reason I say 4 because the pKa for this drug is 4. So if you remember from Dr. Gunasilan's notes, it's whenever the pH is equal to the pKa, you have 50% of the drug ionized and 50% unionized. So when the pH drops below the pKa, then the drug becomes can become ionized. So when the drug becomes ionized, this bond here is broke, and following a series of reactions, eventually the sulfur atom here attaches itself to another sulfur atom, forming a disulfide bond. This sulfur atom here is part of a cysteine amino acid, which is part of the enzyme ATPase, which is the proton pump. So if this is the proton pump, it has an amino acid as part of it, because as you remember, all enzymes are naturally proteins. So proteins are composed of amino acids. One of these amino acids is called cysteine. It has an HS group, so it binds with the S. It binds with the S here, forming a disulfide bond. This bond is covalent and irreversible, and that's how these molecules, proton pump inhibitors, they stick to the enzyme. They block the enzyme from performing its action. I want you to pay attention to something very important here, which is how this sulfur, which is chiral, breaks and becomes free to rotate around a single bond. This means that whether it's an R or an S, eventually during the process of the activation, it's gonna lose its stereochemistry. So whether it's R or S, it's not gonna matter, and we'll find out later where does it matter, when does it matter for a drug, for these class of drugs, that the R or S can become unimportant in the following few slides. So again, the R or S is not going to affect the activity. Both of them are going to go through the same step. They're going to lose their the stereoisomer feature, and they're going to bind to the enzyme all in the same way and block it. The number here is just the number, the 813 is just the number of the amino acid sequence in this enzyme. I should also mention that this enzyme, the proton pump inhibitor, the proton potassium ATPase, is rich with the cysteine. So for this molecule, which I believe is the omeprazole, it binds to the 813 cysteine, but for other proton pump inhibitors, they can bind to other cysteine residues. So before the activation of these proton pump inhibitors, again, they are not active. As long as the pH is higher than 4, these drugs will be traveling safely through the blood and through the intestine, and we're gonna see why it should not go through the stomach unprotected, obviously, and so it's gonna travel through the intestine and get absorbed into the blood, and of course the pH for the blood is 7.4. So these drugs are going to be safely and peacefully traveling until they reach into the parietal cell, and they are excreted into the canalicculus. Inside the canalicculus, they undergo a personality change. They switch into this viscous molecules because the pH now is below 4, and as we explained earlier, the pH in the canalicculus is less than 2. So these molecules are activated and then they bind to this receptor. This actually feature makes these proton pump inhibitors very unique. They make them highly selective. So they travel in the body peacefully, neutrally, and they are inactive until they reach into the place where they are supposed to be working, and they turned into an active molecules. That's why they are highly selective and they have very few side effects. Okay. Another unique thing about that makes these drugs highly selective is the fact that once they are activated, they are ionized, so they cannot cross back into the parietal cell and cause any damage to the cell. So that makes them even more selective. So these features are all in line with the process that we described. First, they target the enzyme which is only present in the parietal cell, but there is an exception here that I'm going to explain very soon. And then second, these are only activated into a pH below 4, which is only at the parietal cell or the canaliculi of the parietal cell. So they are safely traveling until they reach to that place, and they are concentrated, so they're not able to go back. We mentioned that already. And they are rapidly activated. They are activated close to the place where they need to work to attach the target, which is the proton pump. Once they're activated, they rapidly bind into the pump because they are actually immediately activated into the acidic condition, and the first thing they see is the proton pump, and they bind to it and inhibit it. And they, like we said earlier, they travel in a neutral. They travel safely as long as the pH is not less than 4. So the pH of the blood is 7.4, so they should be safe. The point I wanted to mention here is that there is another enzyme called the H plus K plus ATPase that is very similar, has a high similarity to the H plus K plus ATPase, and this second enzyme is actually present in the osteoclast, which is, I think, kind of type of bone, and this enzyme is responsible for the resorption, which means the degradation of the bones back into the blood. If you would like to remember your physiology, the bone goes through a cycle of osteoclast and osteoblast, where you have process of the building and destruction of the bone. So when there should be imbalance. So if one of these is basically inhibited, then it affects the other and leads to fractures. And that's why in 2010 the FDA agency revised the prescription and OTC labels for the proton pump inhibitors to include a safety information about the possibility of increased fractures of the hip, wrist, and spine with the use of these medications. So basically causing osteoporosis. The risk increased mainly in patients of 50 years old and older. So this is just something to keep in mind. But you should already know the limitations of the use of these products. OTC, no more than don't quote me on that, but no more than a few days, or maybe for the proton pump inhibitors no more than 2 weeks, I think. But again, this is not my field. I'm sure Dr. Liu will be better to answer this question better. Basically, the limitations of the use of the proton pump inhibitors, how many days they should be used and when they should be stopped. Okay. Let's talk about the metabolism for proton pump inhibitors and some drug-drug interactions. Omeprazole is primarily metabolized with the enzyme CYP2C19, and therefore it competes for this enzyme with other substrates and drugs like warfarin and some of the benzodiazepines such as the diazepam, methotrexate. So if they are taken at the same time, then they compete for this enzyme, and then eventually the concentration of these products are going to increase. We have discussed the drug-drug interaction in previous session. You could review that, or let me know if this is not clear to you. And then another substrate for this enzyme is the Plavix. Now, Plavix is actually a prodrug. So if you remember, in one of these applications, we had a prodrug, and then when you inhibit the enzyme that metabolizes this drug, then it's not going to be converted into the active form. So it's going to stay inactive, and then this product is going to be actually the effect of this product is going to be reduced. Okay, so it's like the opposite of what you would expect here. Here you have increased the concentration of these products, and therefore the pharmacological effect will increase. Here, in the case of the Plavix, which is an anti-platelet drug, it could actually reduce the pharmacological effect. And we had application of that. If you are not sure about that, I still remember the student who answered this question, Katie or Catherine Freeman. She might be able to answer this question for you. Anyway, so the lansoprazole is metabolized by analogous routes, like similar routes, but there are also substrates for this enzyme. So fewer side effects are observed with the lansoprazole. So if you have to choose between omeprazole and lansoprazole, and you are worried that the patient is taking up these medications, you could consider the lansoprazole. Okay. And this structure here is just to show you some of the sites where this enzyme works. So you could see that this drug is mainly metabolized with this enzyme here. This is the omeprazole, of course. It's mainly metabolized or oxidated by this enzyme, the CYP2C19, and it is metabolized, oxidated by this enzyme only to a lesser extent with this enzyme. Okay, the CYP3A4. Okay, next let's talk about what's called chiral switching. You probably have seen some cases in the past where you would have a drug that is a racemic mixture of two isomers, and then we would exclude one of them because it's inactive and keep the other one because it's the active form, and this process is called chiral switching. Actually, the process is more like for pharmaceutical companies where they decide to market another drug that was marketed previously as a racemic mixture of both isomers, and then now in order to extend the time on the patent that they have, they market another drug under a different name, and they actually basically extend the patent for a new drug that would be one of the enantiomers, which is the active form. Now, problem with these, not problem with the chiral switching, but in general, anytime you have racemic mixture, typically what happens is that one of them is active, another is inactive, or one of them is metabolized more than the other, or you might have one that has better distribution than the other, whatever the reason is. Sometimes you might have one isomer preferred over the
the second one, and therefore you would prefer to switch into using only one isomer. So why didn't we do this from the beginning? Why didn't we just market the one that is more active instead of marketing two enantiomers, like in the case of the omeprazole or any other drug? Like why did we start by marketing both isomers? Why didn't we check for one over the other? Well, back before in the 80s, the synthesis of the isomers was more difficult, so they did not want to spend much time synthesizing and extracting the enantiomers from each other and finding which one is active. But now it is much easier to actually synthesize isomers and extract them and test them. So drugs that were discovered before the 80s, they were racemic mixtures, and their manufacturers now are switching, using the chiral switching to market another drug. But nowadays drugs are supposed to be either achiral with no chiral center or have a pure enantiomers. Whenever we have a racemic mixture of two enantiomers, if one of them is active and the other one is not, the inactive form that is discarded or removed is called isomeric ballast. So this is a term, isomeric ballast, that we used to that we use for the enantiomer that's inactive. Okay, that's the enantiomer that we actually would remove, and then we'll keep the other enantiomer, the active one. Okay, so let's see how this is related to the proton pump inhibitors, the chiral switching. So if you remember, in the process of the activation for the proton pump inhibitors, we mentioned that the sulfur here, which is chiral atom, during the process of the activation, this bond is broke. I'm not sure if it's this or this one, but anyhow, one of them is broke, and then the isomerism is lost. So whether it's an R or an S, both are going to end up binding to the same to the proton in the same way and blocking it. So both enantiomers are equi-active. So both enantiomers are equi-active, whether it's R or S, they bind to the same receptor in the same way. So why does it matter then to switch one over the other? Why did we have the omeprazole and then switched the Prilosec and produced another one, which is the Nexium, the osmeprazole, the S enantiomer? Apparently it matters for metabolism. So the R is actually more extensively metabolized by the enzyme. After all, the enzyme is just a receptor, just like any target. So when it binds to one of these enantiomers, this enzyme, the metabolic enzyme, prefers the R enantiomer. Because it prefers the R, it metabolizes it better. So now we are gonna administer the S. This way we make sure that the drug stays longer into the body and has a better bioavailability. Plus, there's another important point, which is for some people this enzyme could be acting faster than another. So we have fast metabolizers and we have slow metabolizers. So by providing the S, we are actually making sure that that both the fast and slow metabolizers are not going to have a much difference in the way they metabolize the drug. If we provide the R, then you're going to see a variation between the slow and the fast metabolizers. And indeed, you would notice our studies have shown that that the S enantiomer was, I think it was 3 point, let's see. Yep, here we go, threefold. So the difference between the fast and the slow metabolizers using
the S versus the R, you would notice a threefold increase for the area under the curve. So that's why the S is actually preferred and is used. I just want to mention that the slow metabolizers populations are actually available in 3% of Caucasians and up to 15 to 20% in Asians. So again, by providing the S, the inter-individual variation between slow and fast metabolizers will have a less impact, okay, unlike the case we have R. Now for the lansoprazole, it's the opposite. So basically the enzyme prefers the S over the R, and that's why we provide the R and we market it under a different name called the Dex lansoprazole, which is, I think, Dexilent is the name, the brand name for it, which is actually a prescription drug. Okay. That's all. Okay, one last thing about the chiral switching of proton pump inhibitors, which is, what about the other products? So we spoke about the omeprazole and the lansoprazole. What about the pantoprazole and the fourth one? We got its name. Well, the other two are actually the significance in the isomers are not of a big factor, yet outside of the United States there has been some pharmaceutical companies who actually manufactured both the R and S and preferred one over the other. Okay. So one more point I want to add is that the chiral effect, the stereoisomerism effect, in this class of medications would improve the pharmacokinetic profile, not the pharmacodynamic. In other ways, because the R and S have equal activity, they do not affect the pharmacodynamic properties, but because they are metabolized differently, they affect the pharmacokinetic properties. So you would see an improved pharmacokinetic profile by switching from racemic mixture into the preferred enantiomer. Okay, let's talk about an important topic here, switch gear and talk about something else about the proton pump inhibitors, which is the need for the delayed release formulation. Now, you have noticed that the proton pump inhibitors are inactive, they are prodrugs, and they are activated at pH below 4, right? Okay, so what happens if we administer the omeprazole through the stomach where the pH is less than 4? So you would imagine first that by administering the omeprazole, let me move to the other slide actually. Okay, so by administering the omeprazole directly into the stomach where the pH here is 2, which is below 4, the omeprazole is going to be activated. So initially you would think, well, this is what we needed, right? It's activated, now it could bind to the pump and prevent it from producing acid. Well, apparently if it's activated into the stomach, it's going to bind to the first protein that it's going to hit, and this protein could be actually part of a food or could be something else. And indeed it was found that the ability of the omeprazole to bind to the pump if it's activated inside the stomach is very low. It's actually it's reduced significantly. So what is the alternative? The alternative is we administer the omeprazole and actually all these proton pump inhibitors into an enteric coated. This is something that you should learn from Dr. Gnasilan and Dr. Talukdar. What does an enteric coated mean? So these drugs are administered into an enteric coated form, and this is called the delayed release form, such that they pass, in this we're talking about the blue line now, So they passed through the stomach, through the pH protected, they're not activated, okay? So at pH 2, which is less than 4, they're not activated, and they go through the duodenum. The duodenum here, pH is 6, and then it's after they pass through the stomach that they get that this coat is removed, and then the omeprazole or whatever, the proton pump inhibitor, is actually released. And then now, because they are lipophilic, they are still in neutral because the pH is 6, right? So it's above 4. So pH is 6 or 7 in the duodenum and the intestine. They are absorbed and they are now in the blood. They are still in neutral. They are at pH 7.4, so they are fine. They are not activated. They circulate into the blood and they reach into the parietal cell. After they reach into the parietal cell here, they are excreted into the canaliculi, and that's when the personality change happens. At pH 1, they become vicious and they are activated, and now they attack the pump here and inhibit the release of the acid. This here shows the lining of the stomach, and this is, I can't remember what's this name in physiology, but that's fine. This is the parietal cell. It excretes the acid and then it goes into the stomach. So by reaching this way from outside, we make sure that that higher percent of the drug is actually only activated in this part. So this is an important fact where we have to include the enteric-coated form for providing the oral dose form. So can we formulate the drug and administer it by injection? Yes. If you are in a hospital, you could administer the drug directly into the IV, into the blood, and the pH of the drug is 7.4. There's no problem. You don't have to worry about the enteric-coated or anything like that. Okay.
Finally, I just wanted to show you some pictures for these over-the-counter medications to explain to you, to confirm what we discussed. So for the Glycic, you can see that it's mentioned here, delayed release tablets. You will see that all these formulations should be provided in a delayed release form. For the Prevacid also, you would say delayed release. The same for the Nexium, delayed release. What I want you to pay attention to is that there's a difference between delayed release and extended release. I hope you know this by now. If not, I'm sure Dr. Gunasilan or the doctor are going to explain this to you. So anytime we have an enteric-coated, it means delayed release. Sometimes the first thing that comes to your mind when you see 24 hours and delayed release, you might think it's an extended release, but they are not the same. Okay, and that should end our class. That should end our lecture for today.